right? You have to do some independent research, I think. So what we're going to be talking about today is the chi-squared test for independence. And the whole point of this test is to prove if two things are independent or not. We've talked about independent variables and probability in chapter 7, and that's kind of what we're looking at here. So there's something called a null hypothesis, which is denoted by H sub 0, or it's H naught, okay, but we call it the null hypothesis. And normally the null hypothesis will always be like we'll say event A and event B are independent. All right, event A and event B are independent. And then the alternative hypothesis then would be, I'm going to do that in a different color actually. The alternative hypothesis is just event H1, and that is event A and event B are not independent. Okay. That's the alternative hypothesis. So every time you write a null hypothesis, that's what you're basically trying to prove. Hey, are these two things independent? And then we have H1, which says they're not independent. So that's the other outcome of this testing, okay, the test for independence. Okay, so the next part talks about this probability P, and it's obtained from your calculator, so you can do this on your TI-83, TI-84, all right? And the p-value is going to be basically a percentage. It's going to range from 0 to 1, and that's what I want to put down here as well. So the p-value is a number between 0 and 1. And again, it's a probability, basically. All right. They're always going to be expressed as a decimal. Excuse me. Although they may be more easily understood as a percentage. So maybe better understood as a percentage. I'm gonna work on that. All right, so I mean, just for example, you could say 0.1, that's the same as 10%, right? Just thinking about, it could be expressed as a decimal, but it might make more sense to us if we think about it as a percentage. And usually what happens is when you get this percentage, you'll say like if I get 10%, that would say the null hypothesis fails 10% of the time. Or if I get a 0.1, that's what this p-value is going to be telling us when we're doing these types of problems. All right. Okay. So how does p-value relate to Spearman's? That's what we're going to talk about next. So the p-value p-values are determined by observed correlation. So we talked about RS yesterday, so the RS value and sample size. whenever we're doing hypothesis testing, we need a large sample. It can't be a small one. So it's usually more than 10 data points. So we're going to deal with long lists, things like that. Usually that's the best for our hypothesis testing. We can do it with smaller ones, but usually we want to deal with large testing. It's more likely to fail if we don't have a large sample size, because you can't necessarily prove independence with smaller samples. Okay. Let's see. Getting tight on space. Small p-values are strong evidence against the null hypothesis. And we'll talk about that down below. And we just say with a small p-value, we reject the null hypothesis. With a small p-value, we reject the null hypothesis. And we'll talk about what type of values those would look like now. So this is typically how it's going to work. For IB class, we're going to look at what's called statistical significance, and that's referring to p-values. And we're going to be talking about statistical significance is always given in a percentage. So statistical significance at 1%, at 5%, at 10%, or basically when a p-value is 0.01, 0.05, or 0.10. Okay, so we'll start with the p-value. If the p-value is more than 0.1, so more than 10%, right? That would be greater than 10% if it was based on percentage. And then we would say the evidence for rejecting evidence for rejecting the null hypothesis. When it's more than 10%, we're going to say it's very weak, actually. Not just weak, but very weak to none. So which basically means if you get a p-value greater than 10%, then that means that your two events are likely independent events. All right, they're not, one's not causing the other. Okay, that's what this testing is trying to prove. You could have a p-value that is between 0.05 and 0.1, which is 5% to 10%. We'll do that in red. All right, so 5 to 10%, that's still pretty weak. All right. It is possible in the IB exam they'll ask you for a 10% significance factor, but usually we're not going to worry about that. Usually it's more like 5% is when we start to worry. If you're between 1% and 5%, that's what this represents here. That's actually a very strong case to go ahead and reject the null hypothesis. Strong case. And then the last one is if you have less than 0.01, give me less than 1%, then you have a very strong case. For rejecting the null hypothesis. Oh, man. Ooh. I just got a very good email, but it says confidential until 11 a.m. That means you guys are going to get an email at about 11 a.m. Check your inboxes. It's a good one. Okay? Just an FYI, I'm excited for you. I'm already excited for you. This is so exciting. Yay. Okay. Sorry, I can't tell you. Just leave you on that cliffhanger. It says, the very top in red, it says, this message will be delivered to our community at 11 a.m. Please consider the contents to be confidential until our community receives the message. We get those about twice a year, and they get pretty pissed if we spill the beans ahead of time. Yeah. Aaron, you are incorrect, but I like your thought process. Yeah. We're still out of school until February 8th. Sorry. Anyway. All right. Okay. So those are some important things. And right now it's all just terms. We haven't really talked about like an example yet. So let's go ahead and look at an example, and we'll kind of talk about what to expect for these types of problems. So
wait, check the chat.
Yep, check the chat. Okay, yeah. All right, I'm just we're starting at 9:30. I like that. All right, yeah, yeah. Just saying that. Yeah.
Why would you leave us on such a cliffhanger? That's just rude.
Oh, I know, it's so exciting, yeah. All right. Well, like I said, I can't tell you anything, but if you've ever been involved in any after school activities, I don't know, anything like that, that was canceled this fall, that might be ending soon. If you know what I'm saying. Okay? So that's my hint for you. All right. So let's take a look at this first example. This is from exercise 8B in your textbook. This is problem number 1 from the exercise. I'm going to assign problems 2, 3, and 4 to you guys, and they're the exact same type of problem as this. All right, just different data. So it says Misty was interested to find out whether preference for car color was dependent on gender. So again, preference for car color is dependent on gender. And the word dependent is even used there. So if I were writing a null hypothesis, I would say car color is not dependent on gender. Or I could say car color is independent of gender. Is chosen independently of gender. Does that make sense? Independent is what the null hypothesis is trying to prove independence. So we always kind of write our null hypothesis to be kind of the opposite of what the question's asking. And then we can say the alternative hypothesis is car color is dependent on gender. All right. So the first part here, parts A and B, they both say show that. Show that, I've mentioned this before, that's a big term used on the IB exam. And that usually means I can put this in my calculator and not show any work, but it's telling me specifically to show that. So what that means is I just need to show the setup before I put it in my calculator. All right, I'm gonna grab my calculator real quick because I will need it today. So what we need to do for this one is to show the expected number of males who prefer black cars is 10.45. So it's giving us an expected value. It's saying the answer is 10.45. We just need to prove it. So what you need to do for this one, you're looking at males who prefer black cars. So what we're going to need to pull that off, let's see, number of males who prefer black cars. We're going to need the number of black cars, the total number of black cars, and we're going to need the total number of males. Those are the two things we need. And the last but certainly not least, we need the total. All right? So what's happening is we're adding all the colors of the cars vertically. Horizontally, we're adding the males and the females. And then the bottom right-hand corner is the total number of participants in the survey. So there's 80 total participants, which I said normally we want our sample to be bigger than 10. So 80 is way bigger than 10. That's a good thing. So what we're going to do first is we're saying there are 38 males out of 80 total people. There are also 22 people that have black cars out of 80 total people. Okay. So 38 divided by 80, 22 divided by 80. That's going to give us the probability that you are a male with a black car. Okay? That's the probability of a male with a black car right there. Now, to get expected value, I need to multiply that by the total sample. So I'm going to highlight this again. This red part that is the probability that you are male with a black car. This next part, oh, hey, green. That's going to be our total sample size. You multiply by the total sample to find your expected value. And if we do it correctly, we should get 10.45. So 38 divided by 80 times 22 divided by 80 times 80. And we get 10.45. Checks out. All right. Again, the show that means I just need to write down the work that I'm putting into the calculator. Calculator's going to do all the work. I just need to put it in, or write it down real quick beforehand. That's what this first problem looks like. On your homework, the first 3 homework problems are going to be these exact type of problems. Show that, then find chi-squared value. And we're going to talk about how to find the chi-squared value in a minute here. Okay? So now, the female one, let's see, it says the expected number of females who prefer white cars. So we just do the same thing, females, white cars, and our total. Those are the numbers we need for this particular problem. So there were 42 females out of 80. 18 out of 80 prefer white cars. That's going to give us our probability of females that like white cars. And then we multiply that by 80, and we should get 9.45. All right, whenever you have a show that problem, you just need to write down those steps right there, and that's it. And then throw it into your calculator to verify that you did it correctly, that you set it up correctly. And we did. Perfect. Good, good, good. All right, now chi-squared. So what we're going to do for chi-squared is, oh, I put it in the wrong spot. I put it down here. It says in examinations you will be asked to, this is an exam hint, you'll be asked to use your GDC to find this value. So basically what you're going to do for chi-squared is you're going to go to the matrix, you're going to enter the number of rows and the number of columns, not including the totals row or the totals column, and then enter the data and store the matrix. Then you're going to go to your stat tests, you're going to click on the chi-squared two-way test, and you're going to hit enter. All right, so that's how we do this. There's also on Canvas today, I did put this up on Canvas, So you can go up there and see the calculating instructions from your textbook as well. But what we're going to do is we're going to look at this data and say, okay, how big is this matrix? We're not going to include the totals. So theoretically, it's going to be right there, right there. And whenever we're doing a matrix, we talked about this, let's see, exactly, I think one time last year. We might have done this right before Thanksgiving last year in IB 1, Math 1. But basically, the matrix is going to be rows by columns. If you've ever done a programming class, you might know that. And right now, there's row 1, row 2. One for male, one for females. So this is a 2 by, and then the columns are white, black, red, and blue, 2 by 4 matrix. That's what you're going to do in your calculator. So now to get to your matrix in your calculator, there's a matrix button down there. It's a second matrix. And it's going to say names, math, edit. Names, math, edit. And you're going to scroll over to edit. Sorry, I'll give you guys a second. I'm going fast. Okay.
Wait, do we go on the row that says edit, or do we go on the one that says math? Or do we go scroll down on math to find edit?
No. So what happens is it says x to the negative 1 power. You're going to hit the blue button and go x to the negative 1 power. And it's going to give you names, math, edit. You're in the matrix mode now. And you're going to go over to the one that says edit.
Okay, thank you.
And it's going to have the matrices. It's got matrix A, matrix B, matrix C, matrix D, matrix E, etc., etc. You can just go to matrix A, and you're gonna make matrix A 2 by 4 is what the first thing it asks you to do. So that's why it's really important. It's always gonna be rows and then columns. And I gave you a lot of practice on this homework assignment over the weekend, specifically to practice this. We're gonna be doing chi-squared this weekend, and we're gonna be doing it again next time on Monday on 8.3.
Yeah, I checked the homework. There's 4 pages.
Yes.
You went off on the homework.
The homework is the homework's got a few problems. They're just kind of long, but I think they go quickly. They just take up a lot of space. But the homework's just going to ask you, enter the data in your calculator, find chi-squared. Enter the data in your calculator, find chi-squared.
Shows. You click again. Sorry, I got kicked out of the meeting.
Oh, that's fine. So what you're going to do is on your calculator, there's the x to the negative 1 button, and you're going to hit second and x to the negative 1. It says matrix above that in blue. And you're going to get into this matrix column, names, math, edit. And you're going to say edit, and you're going to create a 2 by 4 matrix. And then down below, you can enter the numbers exactly as you see them in the example. 6, 14, 10, 8, 12, 8, 9, 13. And now when I quit, I got my matrix saved. What I can do now is I can hit matrix, and it says names on the button, and I can just click on matrix A on the names, and then it should pop up on my home screen. So again, once you have it entered, go back to the matrix and hit names, and just select your matrix, which was probably matrix A. And it should pop up on the home screen, and you just check your work on your paper to make sure it's entered correctly in your calculator. 6, 14, 10, 8, 12, 8, 9, 13. So I have mine entered correctly, which I'm feeling good about. Okay? That is matrix A.
So I'm at I have it inputted now, what do I do?
Oh, that's a great question. I was just gonna stop and then call it a day, but I guess since you're asking, we might as well keep going.
Yeah, I'm just a little curious.
Yeah. So now you have your matrix. What you're going to do now is you're gonna hit the stat button, and you scroll over to tests. And you're gonna scroll down, and you're gonna look for the chi-squared test. There's 2 of them in there. One of them says chi-squared test, and one of them says chi-squared GOF test. GOF stands for goodness of fit. That's what we're doing next time. So don't use that one. Use the one that says chi-squared test. And it's going to say observed, and it's going to have, you put your own matrix in there, which is matrix A. it's going to say expected, and you're just going to let expected self-populate. It'll just say it'll say matrix B. There's nothing in there, but it's gonna do its own magic and figure it out for you. And then you're gonna hit calculate. It's gonna give you chi-squared value, which looks kind of like an x squared, and then it's gonna give you a p-value, and it's gonna give you a df. Okay. So for this problem, our chi-squared came out to 4 point.
How do you clear one of them?
How do I clear?
I have 2 on accident.
Oh, how do you clear a matrix?
Yeah.
You have to hit the delete button up here. Delete, 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 delete. It has to be the delete button, and I think you delete each one individually. All right, so now you should get your values, and you should get a chi-squared value.
Like, I can't clear it. It says that I have stuff in B. But, like, how do I get rid of the...
Oh, so if you go back to edit, and you click on matrix B, I think you can just hit delete the entire matrix. I think that's what I think that would work. I could be wrong.
It is not.
Okay. We'll have to work on it a little later then. I'll see if I can help you figure it out. All right, so you get your chi-squared, and you're going to get a p-value of 0.19, which is basically 20%, which tells you that this null hypothesis is true, that these are independent events, that your gender does not determine whether you're picking up a car or not. So we end up with this 4.69 for the chi-squared value. All right?
Which number do you, or which thing do you press after you went to stat and tests?
Okay, so you hit stat and you go to tests, and then you scroll down to like the letter C, because the letter C will say chi-squared test and it looks like an X, and the letter D will say chi-squared goodness of fit test, and we don't want to do the goodness of fit test. We want to do just the chi-squared test for right now. And that's going to give us the chi-squared value. It's going to give us the p-value, and it's going to give us df, which stands for degrees of freedom. All right. Okay. So there are some yellow boxes here from your textbook. Let's talk about those briefly. The first one says the formula for degrees of freedom is you take the number of rows minus 1 times the number of columns minus 1. So for this example, the matrix was 2 by 4. So to find the degrees of freedom, you're going to say 2 minus 1 times 4 minus 1. And what that really is, whoops, that's going to be 1 times 3, or just 3. So your degrees of freedom is 3. All right, and it says in examinations, V will always be greater than 1. Your degrees of freedom will always be greater than 1. And so your textbook does not explain what degrees of freedom are, which makes me think that it's not really important that you know exactly what they are, but let me give it a shot. Degrees of freedom are basically everything that should be independent of one event happening. So, for example, you have 4 options for cars: white, black, red, and blue. Right? I think it was blue. Yeah, white, black, red, and blue. So what happens is, let's take away the option of you selecting a white car. Now you independently have 3 more events to choose. That's really what the degrees of freedom are representing, that you have 3 independent events of the first one. So it's usually going to be like 1 degree less than, it's going to be 1 value less than all of your selected options, basically. That's the best way I can describe degrees of freedom in a nutshell without trying to confuse you, because your textbook doesn't make a big deal out of it. But it will ask you to find degrees of freedom. If you do the chi-squared test, it'll give it to you. If you need to show your work on how to do it, you're just going to do the rows of the matrix minus 1 times the columns of the matrix minus 1. All right, so if you need to do it by hand, that's how you do it. All right, and then here's the chi-squared test, where it says you're going to take your observed values, which are the values from our matrix, and you're going to subtract the expected values, which is basically what populated in matrix B on your calculator. And you're going to square those values, and then you're going to divide them by the expected values, and then you're going to take the sum of all of them. And that's what your calculator is doing. That's what that test says. There's another vocab word that your textbook throws in at you. It's something called a critical value. And the critical value can be explained down here in this next yellow area. Again, it doesn't explain what a critical value is, basically. So I'm not going to go too much into it, but essentially, and you're on the IB exam or on your in your textbook, it'll say, "Hey, here's the critical value." It's going to give you some weird number, and if chi-squared value is less than that critical value, we're going to accept the null hypothesis. If chi-squared is greater than that critical value, we're going to reject the null hypothesis. All right, and it's kind of the same thing with the p-values. I'd rather focus on the p-values myself. I think that's a little easier because you can use either the statistical test statistic and the critical value, or you can use the p-value and the significance level. All right. So this is saying p-value is greater than 0.005, and that's your significance level. And there's a note here that says the significance level can be 0.01, can be 1%, 5%, or 10%. So we'll say this right here. Significance level, 1%, 5%, 10%. Those are the three that you'll only be asked about in this course. You're either at a significance level 1, 5, or 10. So basically, if I say, hey, test this thing out on a significance level of 10%, you want to get a p-value above 0.1, so that way you can accept the null hypothesis. That's what that means, okay? Kind of weird. I'm throwing a lot of weird things at you today. I know I'm throwing a lot of weird things at you today. This is really a weird one. Spearman's, I think, was pretty straightforward yesterday, hopefully, with just ranking them and then finding the Pearsons. This one's a little weirder, all right? But you should be able to build a matrix in your calculator. You're going to get a chi-square value. You don't need to know what that value means. You just need to know, is it less than the critical value? And again, you don't need to know what a critical value is either. You just need to know, is this number less than that one, right? And that's the idea here. Okay, so, and it says on the exam, you will be only expected to know 1%, 5%, 10% significance level. And it's always going to be given to you like this. Hey, a chi-square test is carried out at 1% significance level. So that's going to be a 0.01. So we want the p-value to be higher than that. Write down the null and alternative hypotheses for this problem. And the problem says...
How do you know that it's 4.01?
How do I know what?
That it's 4.01.
That what's 4.01?
You wrote down 4.01 for the 1% significance level.
Oh, I just wrote 0.01.
Oh.
That's an arrow. Sorry. Sorry. My terrible handwriting. Let's try that again. We're going to draw a little arrow from there. Arrow. And we're going to say 0.01. Yeah. Okay, so I'm just turning that percent into a decimal. Write down your null and alternative hypotheses. So the null hypothesis for this one, it says 80 people were asked for their favorite genre of music. The results are in the following table. So the null hypothesis is that your taste in music should be independent, basically, right? That's what this is trying to say, okay? So it shouldn't matter whether you're male or female. It shouldn't determine your taste of music, all right? So your favorite music is independent of gender. It's always a safe bet when you're writing a null hypothesis to use the word independent. And that means your alternative hypothesis is your favorite music is not independent of gender.
You have to say independent and not independent and dependent or not
Dependent?
No, I could say independent for the null hypothesis, and then I could say dependent for the alternative hypothesis. That's perfectly fine. All right? So that works. As long as we always use the word independent and the null hypothesis. The favorite music is independent of gender, which is just saying that it doesn't matter whether you're a boy or girl, that does not have an impact on what type of music you like. That's the idea here. Part B, show that the expected value for female liking pop is 21. So female liking pop music. So we're going to look at the totals for females, the totals for pop music, and then our total. Okay, so hopefully we get good at this one. So 40 out of 80, 42 out of 80. Show that means I gotta write this step. And then my total sample size was 80 in this example. And that should equal 21 if I do it correctly. So the last part's just basically double check to make sure I did it correctly. They gave me the answer. The answer is supposed to be 21. Now let's prove that it is 21. I'm going to fix that 80 down here because that's ugly. Okay, so expected value, bam, we got 21. We're feeling good. I like that. Okay. Now, part C, write down the number of degrees of freedom. So we have to determine the size of the matrix, which we're going to need to do for the chi-square anyway. This is 2 rows, 1, 2, 3, 4 columns. So it's a 2x4 matrix. Degrees of freedom is at like lowercase v. It's going to be 2 minus 1 times 4 minus 1, which is 1 times 3, so 3. That's our degrees of freedom. Okay.
Where did -1 come from? Am I like crazy? I don't remember where that came from.
Oh, so yeah, it's from your textbook up here. It just says, oh, by the way, the degrees of freedom, you just do the number of rows minus 1 and the number of columns minus 1. And the reason you're doing -1 is basically you're saying we're going to take like the 4 types of music, pop, classical, folk, and jazz. And we're going to start with pop. And then we're going to say the other 3 types of music are not dependent on that. So that's why we come up with the degrees of freedom being 3. It's always going to be like kind of 1 less than your total number of categories. All right, find the chi-squared test statistic and the p-value. So you go ahead and enter this into your calculator, a 2x4 matrix. All right, and then you go to the chi-squared test, and it's going to give you the output and the p-value. You could edit the previous matrix you did. You could do a completely different matrix if you wanted to. Like I'll go ahead and make matrix D a 2x4. And then I'll enter my data in there.
It's just straight. If you were to use like matrix A, you know how you said like it changed matrix B like
Yes.
magically?
Mm-hmm. Magically.
How would we delete that so it doesn't affect our next go at it?
Because did you try and do it and it gave you an error message or something?
No, I'm just seeing that my matrix B is changed. So does
Okay.
that affect?
Yeah, that's a good question. You know, I don't know what your calculator would do with that. So why don't you try it? Go ahead and change your matrix A and leave your matrix B as whatever it was before, and then try it. But
Okay.
I don't think it should have an impact. I think it should work still.
Okay, thank you.
Yes. Great question. All right, so we got our matrix entered. Now we're going to get stat, tests, and I'm going to roll down again to my chi-squared test. Like for me, I entered it in matrix D, so I'm going to do matrix D this time, which means I just have to type in the new letter. Oh man. All right, and then you should get your values, and you're just going to write down your chi-squared value. You should get your, I think my chi-squared came out to like 1.622, and my p-value 0.654
Wait, I got 10.7.
for your chi-squared.
Yeah.
Okay, so did you check your matrix first to make sure that you had entered correctly? So make sure that you have the matrix entered correctly, 18, 9, 4, 7, 22, 6, 7, 7. So I'd start with that. Okay, and when you do this as well, you should also see the degrees of freedom written down. It should just say 3 down there, which verifies that you did the degrees of freedom correctly, which is good.
I wrote 2 instead of 22.
Aha, there it is. So hopefully that helps then, and that makes the difference. And then part D, or part E, we have the chi-squared. Oh, I forgot to show you this at the beginning. It does say the critical value for this test is 11.345. They just give you a critical value and they gave you the significance level. So the last part is to say 1.622 is less than our critical value of 3.45. So that means we accept the null hypothesis. All right, because it's way less. Or we can look at the p-value and say 0.65 is greater than our 1% significance level, so we accept the null hypothesis. You're never going to get an example where one of them works and one of them fails. You just need to be able to prove it by demonstrating one of them, okay? So then you can state that my favorite music is independent of my gender, all right, because I was able to accept the null hypothesis. Okay? That's all you need to do for your statement there. That's the idea for this type of problem. All right. All right, so that's what hypothesis testing is. That's the kind of the key for it. We need to be able to put a matrix in our calculator, and then we get our null hypothesis. A lot of times we accept it. Sometimes we might have to reject it. Okay, last example today. Real quick, I have degrees of freedom are the number of values free to vary in the data set. So I have a quick definition of it. Like I said, there's no definition in your textbook of it really. And then something else is called a contingency table is used to summarize relationships of large data sets. So for this next example, we have a very large data set. We've got these heights and weights of dogs. And we have 3 types of dogs. There's the bulldogs. They're classified by their height as pocket dogs, standard dogs, or extra large dogs. The pocket dogs have a height that is under 42 centimeters high. So that's what this is right here, is the height of the pocket dogs. The next one, standard dogs have a height between 42 and 50. So that's the height and weight of the standard dogs. And these are the height and weight of the pocket dogs. And then the last one, XLs have a height between 50 and 58, and those are their weights. So that's what this is. That's why this has so many columns. So what we're going to want to do is we're going to want to create what's called a contingency table, where we're going to take all of our data and we're going to break it down into something a lot smaller, so it's going to be a lot easier to put in our calculator. And that's what part B is doing down here, is this contingency table. And the way we break it down is we say we're going to break down the data by whether they're less than the mean, or they're greater than or equal to the mean. Okay, so what that means is first we have to find the mean weight of the 50 dogs. There's a lot of data to enter, so if you go to our Canvas page, I've put it in Google Sheets for you. So it's done already. So I'm gonna open it up on my Canvas page. Where are we? There it is, chi-squared of independence. All right, so example 3 data set in Google Sheets. Here it is. And that's what I love about Google Sheets, I love about Excel, is we can do this data pretty quickly. All right, so if I want to do the mean of these, all the weights of all the dogs, I'm gonna have to capture all of that. So I would type in my average. For some reason, it doesn't use the word mean, it uses the word average in here. And I'm gonna take my B2 columns, which I think was from B2 to B17. That's
Can you
gonna,
show the screen?
what did you say?
Can you show it on the screen?
Yeah, I'll show you my screen, sorry. So the mean weight, after we type it into our Excel sheet, 44.96. All right. Now, we want to complete the following contingency table. Something that's nice is we have all of these weights, and I want to figure out how many weights are less than the mean and how many weights are greater than the mean. So you could count individually how many numbers are below 44.96 and how many are above it. The other thing I could do is I could use this count if. It's called count if. Oops, I'm going to have to put equals. And this will count the columns for me. And it's an if statement. I don't know if you've ever done any programming in your life. You can use if-then statements. And what it's going to do is it's going to help me count how many data points there are. So for example, if I take the B column, we go B2 to B17. So I'm going to say it's going to count if, I'm going to hit comma, and then I'm going to say, in parentheses, less than, I'm going to put an and symbol because I'm going to pull the data from was it H4? Yeah, H4 is my mean. So basically what I'm saying is I'm going to take a look at columns B2 to B17, and I'm going to say, take a look at each individual value there and see if it's less than 44.96. And if it is, I want you to give it a value of 1. We're going to count it. And we count them, and it turns out, hey, there are 13 values that are weight is less than 44.96. That's a heck of a lot faster than having to count them individually. And then what I can do is I can drag and drop over here. And then I've got my code already in there, except this one says C2 to C17. I'm gonna just need to edit it and say D2 to D18. And I'm gonna count my D column. And it says I4 because it moves everything over 1. So I'm gonna have to turn that back to H4. But now I've got my next one counted. And then I can do it one more time for the F column, F2 to F18. And I'm gonna say H4. So for me, like, I didn't know how to do this yesterday. And I just Googled it and just said, how do I do this on Google Sheets? Or how do I do this in Microsoft Excel? So if you guys, it's a really powerful program, really is. If you ever need to find something in Excel or Google Sheets, there's 99% of the time there's a way to do it. You just have to educate yourselves. And if you get really good at Excel, it's going to help you get jobs eventually. So, I mean, it's not a bad thing to do. And then we can do count if again, except we'll say the next one is greater than the mean. And I'm just going to change this to greater than or equal to. And it's going to give me the next column. All right. And basically I'm filling out what is called my contingency table now. And it's just changing a little bit of code, and you should be able to use all of this from here. Okay. I've never been a good coder. I've taken coding classes. I'm not very good at it. This is pretty remedial stuff. But I mean, it's just very basic looking at this type of stuff. But there's usually always a way to do this on an Excel spreadsheet, which is kind of nice. All right, but I have this data now. I'm going to go back to my other screen. And I was just able to count those faster than if I had to do it by hand, which is kind of nice. Take the time to put it in Excel, and then you can do this and say, okay, well, there were 13 and 3. And then standard, there were 8 that were smaller than the mean, 9 that were larger. And extra large, there were 3 that were smaller and 14 that were larger. Okay? So now we have our data in a much smaller matrix. It's a 2x3 matrix. That's going to be a heck of a lot easier to deal with than trying to deal with all of our data before. So that's why we have this thing called the contingency table. All right, it's going to do this for us, so it makes it a lot easier for us to deal with the data. Now we're going to write the null hypothesis, and we're going to say the null hypothesis for this one. We're hoping that the class of the dog is independent of weight.
Mr. Street, for standards, shouldn't it be 8 and 8, not 8 and 9?
For standards,
Yeah.
it should be 8 and 9 because there are 17 data points, I think, right? So, because notice this one had 16, so 13 and 3 is 16, and then these ones had one more, so these two should be 17 each. Are you saying that there's a weight that's less than 44.6? Let's see, there's 1, 2, 3, 4, 5, 6, 7.
I'm not sure. It's just what the Google Sheet
8.
thing said when I calculated it. So.
Oh, weird. So now I got 8 when I got 8 that's less than 44.9. Yeah, I don't know why. Maybe I did write it backwards. Let's see. Yeah. No, I had 8. Yeah, I just looked at it. Yeah, I had 8. I don't know. That's weird. So the null hypothesis, the class of dog is independent of weight. That means the alternative hypothesis is that it's dependent on weight. Class of dog dependent on weight. Or of weight. Okay, write down the degrees of freedom. All right. So you could do that by saying 2 minus 1 times 3 minus 1. Or you could just, when you do the chi-square test, you can come up with it as well. So, but 2 minus 1 times 3 minus 1, that should give us a value of 2 for our degrees of freedom. And then show that the expected number of extra large dogs that weigh less than the mean is 8.16. So the expected number that weigh less than the mean is 8.16. So what we have to do then is we kind of have to go back to our totals. This one doesn't have a totals table, so we have to add that here. So there's 50 total dogs. Of the 50 total dogs, oops, I'm sorry, 50 should go down here. We should have 13, 8 is 21, and 3, 24 of them weigh less than the mean. And that means 26 of them weigh more than the mean. And then there were 16 pockets, 17 standards, and 17 XLs. And that should all add up to 50. So you have to create your totals, columns and rows. Sometimes they're not always going to be given to you. And the expected number here of XLs was 17 out of 50. The expected number whose weight was less was 24 out of 50. So that's going to give us the probability that your expected number was less than your that you were less than your weight, and you were an extra large dog. All right, and then we say times 50, and that should get us 8.16. Show that, so we should get that value. Part F, find the chi-squared test statistic and the p-value. So we just put that in our calculator. Find the chi-squared test statistic and the p-value. And then finally, part G, comment on your answer. So that's just going to say, we proved the null hypothesis, we accepted it, or we rejected it. All right. So our chi-squared here, whenever I do chi-squared, I'm going to try and do it like it looks like an x but with a big tail on it. That's how I'll represent chi-squared. All right, so chi-squared on this one came out to kind of a big number. I got 13.4. And then our p-value, 0.00125. So less than 1%, which is very bad. Because we were supposed to do a 5% significance test. This came out to less than 1. I guess it's not bad, it just means this is far less than 5%, so we are going to reject the null hypothesis. And this is saying then that the weight of dogs is dependent on their class size. All right, their class size is dependent on their weight, I should say. Okay, that's what this final part's saying. One thing to remember with null hypothesis, there's a saying that statisticians have, which is if the p-value is low, reject the hoe, because it's H0 is the hoe. So if the p-value is low, reject the hoe. That's how you can hopefully remember it, just a little play on words there. All right, so that's for null hypothesis. All right.